So, hi everyone, welcome to today's session on linear algebra to geometry. So, I'm Rupesh Kumar. So, let's wait for a few more minutes so that others can join. Hi everyone, am I audible?
Yes, sir.
Okay, fine. So let's start the session. Fine. So last time what we were doing is we were solving few problems from session 9, week 9, right? So we have already covered all the topics in the week 9. So we have already seen the notes in which we were actually covering all the topics. Let me just revisit, give you just go ahead and go along the titles. So we understood the concept of null space, then what is the range of a matrix, then what is row and what are row and column spaces, then what is the definition of nullity and rank, then what are orthogonal spaces, right? And then how do you define a subspace? Then what are the four fundamental subspaces, right? And yeah, this was it. And based on this we had to solve few problems, right? So let's quickly get to the problems that I have that we needed to finish for week 9, right? So let's start with the first problem, right? So the set of all solutions to the homogeneous system of equations Ax equals to 0, where A is a m cross and real matrix, is called as, right? So question is, you have to find the set of all you have to find X belongs to Rn such that Ax equals to 0. Then uh, let me just reframe it like this. So let us consider X belongs to some set S, where S is a subset of R2 or Rn actually, right? Then for all X such that Ax equals to 0, then for all X belongs to S such that Ax equals to 0, the set S is called, so we know this. This is essentially the null space, right? Null space of A. So option C is correct. Anyone, do you have any doubts in this problem?
No, sir.
Fine. So let's move to the next question. Consider the subspace W is equals to S um 2 comma 3 plus T into 1 minus 7. So it is a subspace of R2, right? So where S and T are arbitrary real numbers, real scalars, then two statements are given. We have to check, verify their correctness, right? If they are correct or not. Fine. So yeah. So let's see. So first of all, the question says these are subspaces. So I hope you can verify that this subspace satisfies all the properties of a vector space, right? Now, statement 1, 0, comma 0 is a basis for orthogonal complement subspace of W, right? So we all know the definition of orthogonal complement subspace, right? So we need to find X such that now we need to find a subset S. We need to find a subset S such that for all X belongs to S and V belongs to W, X dot V equals to 0, right? This is your uh, orthogonal complement set, right? Hmm, right. So let's try to solve this problem. Okay, fine. So now we have a vector S. We can write our X as S. Let me write it like 2S plus T and then 3S minus 7T. So this is a vector that belongs to W, right? This is our V. Now, what would be? orthogonal complement of this. Orthogonal complement of this would be something v1 x1 x2, dot product has to be 0, right? So this will give you an equation in two variables, and this will give you an orthogonal complement, right? Now, is 0 comma 0 a basis for orthogonal complement, right? Is this true?
0 0 will be there. I think it will be there.
Will it be a basis? What is the definition of a basis?
With this, we can span the vector space. With the basis, we can span. No,
Right.
we
So
can reach
can
to
you
the.
span the basis? Can you span something using origin, some
No, no,
space,
no, no.
right?
If you will take 0 0, we can't take.
Right.
Hmm. So that will be false, I think. Then hello.
Yes. Fine. Right. So statement one is false. Then go to statement two. Empty set is the basis of orthogonal complement of W, right? So basically, uh, uh, yeah, right. So, right. So basically, for a basis, the properties are that basis should be linearly independent, right? Independent, and it should span the space, right? Now, you see for the definition of linear independence is alpha into basis alpha I into basis I. If this quantity is 0, then alpha i's has to be 0. All alpha i's for all I belongs to 1, 2, and something, right? Now, let's say if you are choosing 0, 0 as a basis, then you will get alpha into 0, 0 equals to 0 for alpha equals to 1, 2, or basically any scalar k which is non-zero, right? So this cannot be a basis, fine. So now the second statement says blank is no, null set is the basis for orthogonal complement of space of W. Now in this null set there is no vector, right? So basically let's think of what will be the space spanned by W, and then what will be the orthogonal complement space, right? So basically in R2 you have this let's define the basis for W, right? So we can always choose 2 comma 3 and 1 comma minus 7 as basis for W, right? The subspace W. Now my question is, are they sufficient? Are they basis for R2? The question is this. Can anyone tell me? Can you tell me, right?
So that will be treated as a basis. I think if you see, I think by row space we have to take.
Right, but let's see, right? So you have this R2 space. Let's say these are all this space spans and R the auto all R2 space, right? Now the question is, if I have two vectors, 2 comma 3 and 1 comma minus 7, 2 comma 3 and 1 comma minus 7. My question is basically the first thing, these are spanning the space W, right? Some vector space W. The question is, do they span R2, the entire R2? The question is this, right? So how can you check? How can you check this? Since we are dealing with R2 two-dimensional space, we need linearly independent vectors, right? Vectors that lie in R2. And are these linearly independent? Anyone?
Yes, they
It is
are.
linear. Yes, I think it
Fine.
is there.
So
Yes.
from this we can conclude that the vector space W is essentially equivalent to R2 space. Basically, these two vectors are spanning the entire R2 space, right? Then the question is, what is the orthogonal complement of W, right? So now you have to find a vector that belongs to some set S, which is a subset of R2, such that x dot this any vector V equals to 0, where V belongs to W. Now my question is, can you find any such vector? Which vector satisfies this property?
Only zero vector.
Only 0, right? Only 0 satisfies this property, right? So and so basically it's empty space, right? So now if you have some empty space, can you define some basis for this?
Only okay. Yeah. So no non-empty vector would be the basis for it. So it has to be some singleton kind of some empty set. The basis
Right.
also.
So basically, since the subspace contains no vectors, and you cannot choose 0 because again 0 cannot be a basis, that we already saw from the first part, right? Right. So when you check it for the empty space, you don't need any vector to span that space. So basically, empty set can be used as a basis, right? So yeah, so this is a basis for the orthogonal complement of this, right? So statement 1 is false, statement 2 is true. Option A. Anyone do you have any doubts?
No, sir. Clear.
Fine. So let's move on to the next question. Given a non-zero matrix A of size 6 cross 9, so is a 6 cross 9 matrix, right? The question is, what is the rank of A? So what will be the rank of A? No other information is given, and it's the problem statement says at least. So can anyone tell me what will be the answer to this?
Since no other computation is given, no other criteria are given, only zero, I think. No other criteria are given, so we can make all entries zero, and then it will have rank zero. Oh,
It
sorry,
says
non-zero matrix.
non-zero
Okay, one,
matrix,
one.
right?
Okay, okay, one, one.
One.
Right, right.
Fine. So option A is correct, right? Anyone do you have any doubts on this? Fine. Let's move on to the next question. Which of the following vectors is in the orthogonal complement subspace spanned by the vectors this, right? Again, very simple. You just have to pick all the vectors and check which one of these has a zero dot product with both of these vectors, right? So very simple, very straightforward problem. So what you do, first check the dot product with 1, 2, and 3, right? So for option A, just take the dot product with 1, 2, 3, 1, 2, 3. This will be 0 plus 2 minus 6. So this is non-zero, right? So option A is out of the scope. Option A cannot be correct, right? Again, option B, take a dot product with 1, 2, 3. You will get 0 plus 12 plus 12. Again, non-zero, so no. Take dot product with 1, 2, 3. You get 0 plus 8 minus 18, right? Non-zero, so not possible. Then take 1, 2, 3 is equals to 0 minus 12 plus 12, which is equals to 0. This may lie in the orthogonal complement set. Let's again check with the second basis also. So let's check 0 minus 6, 4, dot product with 1, 0, 0, which will be 0. So yeah, option D is correct. Fine, everyone. Is the idea of orthogonal complement clear to everyone? Anyone do you have any doubts? Right. So let's move on to the next question. Consider the matrix A equals to 1, 2, 2. Fine. So we have A equals to 1, 2, 2. We make the following two statements about this matrix. Let's see. What is the basis of column space of the matrix, right? Both of statements says what is the basis of column space of matrix A, right? So let's go ahead and check this. Now we all know the definition of basis. So basis, what is a basis? It spans the space, and basis should be linearly independent. These are two basic properties. Independence, right? So these are two basic properties, right? Now we are talking about the column space of A. Let's check out what is the column space of A. We remember this, right? So let's say A is a M cross N matrix, and for our case, one row and three columns, right? So it maps vectors from R3, right, to R1, yeah, to R1, right? So what will be the basis? The basis of the column space, right? Column space. So the column spaces is basically this output space, right? Linear combination of the column vectors, which are alpha into 1 plus beta into 2 plus gamma into 2, right? So this is essentially a one-dimensional space. So this belongs to R1, right? This belongs to R1. So what is the basis for R1? Anyone?
Any non-zero real number.
Right. Basis for R1. It can be value k such that k is greater as k not equals to 0, right? Now let's go ahead and look at the options. Statement 1, a basis for the column space of matrix A is 2, a vector containing 2. A basis for column space of matrix A is pi, right? So either k equals to 2 and 2 is not equals to 0. Here k equals to pi, right? Pi is not equals to 0. So both options are correct. So statement 1 is true, statement 2 is true, right? Anyone, do you have any doubts? Fine. So let's move on to the last question. Right. So suppose we have a system of equations. Ax equals to b, b is non-zero, and we have a unique solution, right? Have a unique solution, right? Now my question is, when you say Ax equals to b and you have a unique solution where A is a rectangular matrix, right? What does this mean? Right? This essentially usually means is that uh, the number of equations are basically the number of equations and the number of variables are same. That means m equals to n, right? And A is a full rank matrix. A has to be a full rank matrix, right? Now the question says, now let's say x equals to xp is the solution. Then what is the set S equals to xp? So what is the set containing xp, right? Is always a vector space. Anyone? Option A, anyone? Can you say, is it a vector space?
No, sir. Zero is not there. So zero vector
Yeah.
won't be there.
Right.
Sir, I have one doubt. So
Hmm.
why should we consider m equal to n? It might be that there are redundant equations made up of
Oh,
good
right.
equations.
Yeah, right. You are right. Sorry. I mean, the I was thinking that like, m equals to n essentially means number of linearly independent equations are m.
Right,
M.
right, right.
Right, right. Yeah. So A can be any matrix. It just have to be full rank, right? In that sense. Now, yeah, this is right. Is this a linearly dependent set? Again, for linear independence, you can check alpha into xp equals to 0. This implies alpha has to be 0 since xp can't be 0, right? And why xp can't be 0? Can we infer this from the problem statement? Anyone?
Yes, because B is not equal to 0 given. So
Yeah,
otherwise
b is
AXP
not
would have been.
equals to 0. And very important clue that it has a unique solution. This means the matrix A itself is it's not like that b x. I mean, it doesn't mean that multiple values are mapping to one single vector, multiple combinations, right? So this would mean like less number of equations and more variables, but this is not the case. Fine. So
Yes, sir.
xp is not non-zero. Then so it's linearly independent is an element of the column space of A. Okay, column space ax equals to b. No, column space of A is essentially B, right? The space spanned by the matrix B. Well, sorry, column space of A would be, let's say A is m cross n and x is n cross 1. Column space will be m cross 1. So yeah, these are not same. So option D is not correct, right? Anyone do you have any doubts in these problems?
No, sir. Clear up till this.
Fine. So can we proceed, everyone?
Yes, sir. Sure.
Fine. So let's proceed with week 10 notes and the problems, right? So let me cover all the topics that were covered in week 10. Fine. So in week 10, you saw how to solve system of equations for m cross n matrices, right? So let's say A is a m cross n matrix, a rectangular matrix, right? M is not necessarily equals to n, right? Then you have to solve for ax equals to y, where x belongs to the input space of A and y belongs to range of A, right? Column space of A. So what can you infer from this information for these kind of systems? The first information is if m is greater than n, which means the matrix is taller, which means more number of equations than number of variables, right? So tall matrix, right? This is the first thing. Then you can have either consistent system or inconsistent, depending on the rank, right? Inconsistent. If it is rank deficient, then you may get a consistent system. If it's full rank, then it will be for sure inconsistent, right? It is clear, everyone, why it will be inconsistent. You won't get a single value. You won't get a solution for this system of equations. Everyone, do you agree with this?
Yes, sir. Yeah.
Right? So you have no more equations than variables, so it will lead to solutions like this. Let's say this is equation in three variables. These are three equations given in two variables, right? So you do not get a single intersection point, which will be the solution. So geometrically, you can see this system of equations does not have a solution, right? So this is an inconsistent system of equation, and this is what you will observe for these cases, right? You have three equations and two variables here, right? But can you do something? Yes, you can always do. You can always approximate the solution, and you can always use the least square solution. We already know the least square trick, right? So find the nearest vector that is closer to this, right? So this is the first case. Second case, if the matrix is wide, by wide, what we mean, number of equations is less than the number of variables, right? What can you infer some anything from this condition? So basically, if the number of variables is greater, the number of variables is greater than number of equations, what does this mean? This means you cannot get a single solution, right? So for example, let's say I'm trying to solve this system of equations, x plus y is equals to 0, right? So you have two variables, two unknowns, and one equation, right? From this, the solution is x equals to minus y. Now, if you look geometrically to this, you will see this as this line, right? This will be the line that goes through the origin. right? Now this is all the points lying on this line are essentially a solution to this system of equation, right? The entire line is a solution, so you get infinite number of solutions. Fine. So this is very straightforward. If you have a wide matrix, basically number of unknowns as greater than the number of equations, you will get uh, infinite many solutions. Consistency, basically, now whether you get infinite number of solutions or not, that is something that depends on the value on the right hand side, right? Let me give you an example for that. For example, let's say I'm saying 2x plus 3y plus z equals to 1, and I'm saying 2x plus 3y plus z equals to 2, right? Can we solve these systems of equations? Anyone? Do we get infinite number of solutions for this?
We'll get no solution because they're parallel planes.
Right. So these are parallel lines, right? Geometrically, this will form a parallel line, and you will never get a single point of intersection, any point of intersection, right? So basically, it can be consistent depending upon the value of b, right? Depending upon the value of p here. So what is the value of p will define if we get uh, uh if we get a consistent system of not, right? Yeah.
So in option A, I have one doubt. Is for tall matrices, is it always the case that it will be inconsistent, or like we should have an additional criteria with tall matrices?
I mean,
Full
if
rank.
it's full rank criteria is
So,
important.
okay, so suppose I have a matrix of size 5 cross 3, and
Okay.
the matrix has rank 3. So it is a full rank matrix, right?
Yeah, it's a full rank matrix.
So will it always be inconsistent, or is it possible for it to be consistent also?
It won't be consistent, right? No, it won't be consistent.
Why so?
Right. Let's figure out. Let's look into this, right? Fine. Okay.
So actually, you took the exact example which I was thinking. So first the
1
right,
1 0 and
maybe all the combinations one right.
right. So let's say we have this 5 cross 3 system, 5 cross 3, and we want to solve for this. So let's say x, y, z is equals to b1,
Let's say it is.
b2. What?
I can give you the exact numerical. Let's say it is 2, 3, 4, and 2 again, and the sum of all those things. No, the B side. So we'll be solving for x part. The B side
Right.
is 2, 3, 4, and then again 2, and then 9.
Right.
So here it is not inconsistent, right? Because I have chosen the number to be 2, 3, 4, the solution.
Okay, let me see. X, Y, Z, X, and X plus Y plus Z. Right?
Right.
Okay. Right. You're right. There will be 2, 3, 4. Right. You're right. You're actually right.
So along with the full rank condition, what else can we include so that a full rank tall matrix it becomes inconsistent?
Okay, right. Yeah, because okay, let me see here. This is the null space, and you can always write, you can always have anything in that space. Um, o- right. So basically, we cannot deterministically say if we can have these kind of examples. Hmm. Oh, right. Makes sense. Makes sense. Why is this happening? Okay. We will see why is this happening, right?
Okay, sir. Yeah. So we can mark it.
Inconsistent.
We can find out if there exists additional point, adding which we can deterministically say that.
There is a reason why you are getting this solution, right? So the thing is, what happens is, let's say this is your space, right? So this is the what we call column space of matrix, call space of A, right? And you're trying to solve for AX equals to B, right? Now, what happens is when it is stall, then M is essentially greater than N. you you essentially get M is greater than N. So basically, the columns of matrix A, the vectors that belongs to column of matrix A is of time is a 5-dimensional vector, right?
Right.
So m-dimensional vector, right? So you can have m-dimensional vector, but the column space, but the input space, your input space is essentially 3-dimensional, right? So let's see how it looks like. So you have m-dimensional output space, and then, right. So now this is the m-dimensional output space, and the input space is n-dimensional, right? N-dimensional. And you are trying to use a linear combination of m-dimensional vectors. So linear combination of m-dimensional vectors to form and get to a n-dimensional. Uh, right. So right. And so you write like this. So let's say you have vectors v1, v2 up to vn, right? And each vi belongs to Rm for all I equals to 1, 2 up to n, right?
Right.
So now this is your this is the set of your vectors, right? That span the output space of A, column space of A. Now you are saying you can write a vector as alpha I multiplied by vi, I equals to 1 to n, where alpha i's are scalars, right? Now, this can you span an m-dimensional space? So you are trying to span an m-dimensional space, right? So how many m-dimensional vectors you need? The question is how many m-dimensional vectors you need, which obviously linearly independent. How many? At least, basically. How many linearly independent m-dimensional vectors do you need to span the entire m-dimensional space?
M many.
Huh?
M many, right?
M, right?
It is M
M.
dimensional. But
But
so
now,
it boils down to whether B belongs to that. So it depends on the choice of B as well, no? That if B
yeah,
is from the
right.
column space, then we can have the solution. If B is not, then we can't have.
Yeah, right. So you need m vectors, right? You need m
Okay.
linearly independent vectors, right?
Right.
Independent vectors. And since you only have n, right?
Right.
You only have n linearly, which is less than m, linearly independent vectors, right? So there will be vectors that will lie in the column span, there will be vectors that won't.
Okay. Right.
For
So it
example,
has
you
the
are trying to
possibility
ah,
of not having solution and having solutions both.
having solution both. So why this happens? This very simple example is, let's say you are trying to span the R3 space, and the basis the columns of your matrix look like this, right?
Right.
So now what you do, you say alpha beta 0 is the column space, right?
Yes.
Space. So now what does this look like? It essentially is the XY plane. So let's choose XY here and Z as the orthogonal plane, right? So now you can span the entire XY plane. You can span the entire XY plane here. You can span the entire XY plane, but you cannot span the vectors along Z, right?
Yeah.
So anything that goes out of this plane, you cannot span. So this is how it looks like, essentially. And now why we need when do we need the least square solution? When essentially your B is not in this span. So then the system is inconsistent. And then what you do, you can do, there are various ways, but the best approximation is the orthogonal projection. Simple. That is what is being done in the least square solutions. Fine.
Yes, sir. Yeah. Yeah.
So essentially, the matrix is outside. So let's say this is the column space, and this is your vector B. So what you can do, you can at best you can take its orthogonal projection on the column space. That's it. And the vector x asterisk that gives you ax asterisk is closest to B. Closest to B will be the solution. The best possible solution. Least square solution. Right. Fine. And again, if let's say B was on the span, then basically what you would say, you will say that projection of the vector B on the plane is B itself. Now, if the projection of B on the plane B itself is the B itself, then essentially you can have a solution. That's it. That's what it says. Fine.
Yes, sir. Yeah. So, sir, I have one small doubt. In the slide of lecture 46, so sir
Yeah.
mentioned the consistency condition as uh, if a vector belongs to the left null space of that. So,
That I'm coming to this. I'm coming to
okay,
this.
okay, okay, sir. Yeah. So that in there I have doubt.
Hmm. Fine.
Okay, okay.
So B belongs to column. So this was it. This was condition A, right? Then we come to condition B. Wide matrix, again, it depends on B. You can have infinite many solutions, or you can have parallel lines, basically no solutions, right? Right. So what this means, the meaning of infinite many solution is you can represent B as infinite number of linear combination of columns of A. That's it. Or you can say B belongs to the column space of A. That's it. Right. Now the question is, when are these consistent? Can we say something? Can we quantify this thing? Right? Yes, we can. So let's say I'm trying to solve for AX equals to B, right? So then I can say take transpose both sides. You get X transpose A transpose equals to B transpose. Basically, you know the property AB whole transpose equals to B transpose A transpose, right? The transpose of product of two matrices is equals to transpose of second multiplied by the transpose of first, right? Then use in this property. Now let's say we take a vector Y that belongs to the null space of A transpose, right? A transpose. Then you know that A transpose Y equals to 0. Fine. This everyone knows because of the definition of null space of A transpose. Now what you do, you multiply Y on the right hand side, towards the right on both sides of this equation. Ax equals to B, right? Now from here you can say that X transpose A transpose Y equals to B transpose Y. This gives you A transpose Y is essentially 0. A transpose Y is 0. So this gives you B transpose Y equals to 0. Now, if you want to have a consistent solution, you need to ensure that B transpose Y equals to 0, where Y belongs to null space of A transpose. So this is the condition for consistency, right? So, so what's the question, Rohan? Now can you ask?
Yes, sir. So this part was seeming very like uh, very sudden to me, that how someone knew that we have to do in this order. So they are doing in this order, and they are justifying that okay, if Y is coming from left null space of A, then A transpose of Y would be 0. So I'm okay with that. But like, what's the hunch? Why are you going in this direction? We could have gone in any other direction and found a consistency condition. So why suddenly we got to know that we'll pick a vector from the left null space and we'll proceed in this way? Um, Suddenly,
Right.
why? What
That
motivated
is
us?
something that is something related to this fundamental spaces of matrix.
Okay, okay. So
So
is there
why
any way
we
to
do?
visualize it?
Yeah.
Is there a way to visualize it, or like it is very natural to us that will that's why we pick the vector from left null space, or like so
Yeah.
uh,
When
yeah.
you try to look into the properties of these fundamental spaces, you will get to know that this is the natural way to proceed with this thing
Okay,
in
okay.
this direction, right? And also, when you see a system like this, ax equals to b, and you want to ensure that you are whether you are getting a consistent solution or not. So this is one way you can do this. And also the intuition will also look like this. So basically, B belongs to, so let's say A is an M cross n matrix, right? So let's get here. A is M cross n matrix, right? Then the B belongs to range space of A, right? RA, which is RM, which belongs to RM, right?
Right, right. Yeah.
And the null space of wait a minute. Ax equals to B. B belongs to range space of A, right? Huh. And then null space of A transpose. Right. And null space of A essentially belongs to the space Rn, right? So
Yeah.
this everything here is in Rn, Rm. Everything here is in Rm, and everything here is in Rn, right? So you can define operations on vectors which belong in the same space. So you can always define operation between vectors in Ra and A transpose, right? You can always define the operations. And we can prove that our vectors, if a vector belongs to Ra, then it will be orthogonal to vectors belonging to an A transpose. Can we prove this?
Uh, sorry, I missed a small part. Just repeat last portion which you said right now.
I'm
What
saying
to prove?
if a vector belong to range space of A, column space of A, then it will be orthogonal to any vector that lies in the null
Oh,
space
right,
of A
right.
transpose.
Yes, yes, we can do that. Yeah.
Can we prove this?
Yes, yeah, we can do that.
That is essentially the consistency condition.
Oh, okay, okay. Oh, okay, okay. Right.
Fine.
Okay, sir. Yeah, yeah, yeah.
Is this
It makes
clear?
sense now. Yeah. Yes, sir.
Right. So these are the four basic fundamental spaces associated with any matrix, right? So these exist for any matrix. Okay, fine. Now let's move on to the least square solution for the rectangular matrices, where you have basically a tall matrix, right? Let's consider the tall matrix case first. Now we already saw this, right? So let's say you have a vector, you want to span the space Rm, the Rm space, using only n linearly independent vectors. Then you can either get the solution or you will not get the solution, that depending on the value of v. But you can always ensure that a least square solution exists, which is the vector in the column space of A, in the row space of column space of A, basically span of A, um, range of A, right? Span of A, and it will be the nearest vector, nearest to the vector B, right? You can always consider this. So this is we already have covered. Anyone, do you have any doubts in this till now?
No, sir.
Fine. Now, how to get to the solution? It is very straightforward. We all know orthogonal projection by now, right? So if you have, it is equivalent to minimizing this energy term, which is defined for Euclidean space, right? The L2 norm between square root of L2 norm between the vector Ax star, which is vector for x star in domain, x star basically in domain of A, right? In domain of A, such that Ax star minus B is minimized. The vector length, this length has to be minimum. And we all know that for Euclidean space, the distance from a point to the plane is minimum when you take orthogonal projection of the point on the plane, right? Is this clear, everyone? For Euclidean spaces?
Yes, sir. Right. Sir, why
Fine.
you said that energy, how it relates to energy, that minimizing that L2
I
norm?
mean, you can call it energy, or what is energy? Energy is basically, let's ignore that term, but yeah, I can give you an intuition like in how can you say? So let's say if you want to, we all know the energy theorem, right? The system wants to stay at the least energy state, right?
Right, right.
Right? Okay.
Yes, sir.
So Sorry, there was an interruption.
No worries, sir.
My screen is shared, right?
Yeah.
Okay, fine. So basically, what I'm trying to say is why this is an energy, because um, in physics, basically, whenever you want to say where a particle should be, then you always say that it should be lying in the minimum energy state, right? And I think it was in I don't know, in thermodynamics class, like in class 11 thermodynamics course chapter, right? So this is in stable state. This let's say this is energy curve. This forms like this. The part system wants to stay at this state, which is the minimum of the energy. It is
Okay,
something
wow.
related to that,
Nice.
right?
You connected them very nicely. So I thought like I have never thought of them in that way, in energy kind of way.
Yeah, why I'm saying this is as energy, because we actually use in our applications this term as an energy, right?
Oh, okay, okay.
Yeah, this is also this is essentially the least square solution. Linear regression, they use it as a loss function also in
Right.
machine learning application,
Yeah.
right?
Yeah.
Then when you simply expand this equation and minimize with respect to x star, you will get the solution, right? Now you can get to now from there you can always figure out this what the solution to x star should be, right? What this x star should look like, and this will give you the equation of pseudo inverse. Is this clear, everyone?
Yes, clearly.
Fine. So essentially, what this x star this matrix we call it as x dagger sign, right? X dagger sign. This is essentially pseudo inverse. So what does it do? It is essentially projecting a vector onto the column space of matrix A. That's it. So it's a projection
It
matrix.
is
And
a dagger, no, not X
right.
dagger.
Okay, X dagger is the point and A dagger is the yeah, projection matrix, right? So A dagger is essentially projecting any vector onto the column space of the matrix A, right? Anyone do you have any doubts on this? This is
No, sir.
the basically a pseudo inverse, right? So this projection is essentially not a pseudo inverse. Pseudo inverse is this term. So this matrix. So when you take A into this, you get the input term itself. Fine. So let's move on to the
Oh, so one doubt is there, like
yeah.
when we are finding X dagger, like so we are in the both the cases underdetermined or overdetermined. In the both the cases, we have to proceed in this way only, whether it is a column matrix or a tall, means whether it is a tall matrix or wide matrix. So in the both the cases, we have to come to we have to solve by this approach.
So this approach, this solution which I have written right now is for tall matrices.
Okay. Then to for like wide matrices also we can take the transpose and we can have a look on the same way. I think
Yeah,
then we can
always,
transpose.
always. Yeah, you can.
But if we have like if we have more equations than number of variables, or suppose if we have infinitely many solution, then will we to take the this kind of pseudo inverse, or like, because we have infinitely many solution, so why to approximate, because when we have exact solutions.
No, right. That basically, if you have more number of variables than the number of equations.
Excuse me, sir. Here one doubt is there also. Like if it is consistent, no, then I think A dagger will be equal to A okay, no, not A inverse. If it is unique solution, then definitely it will be there. A dagger will be equal to I think A inverse only, no. If it is unique solution, then
A is not a square matrix, so you cannot discuss
okay, no,
deal.
okay.
Cannot.
Inverse we can't do. Okay, this there. Okay,
Fine. Now Rohan, what was your doubt?
Yeah, so my doubt was related to Satyendra's doubt also. So if we have a consistent system, So B belongs to the column space. So we can have solution. Now the point is either unique or infinitely many. So if we have infinitely many solution, then do we do this kind of things, that a dagger or
So
projecting
for
them?
unique solution, you need a square matrix, right?
Not necessary. Maybe
I
redundant
mean,
equations are there.
d- yeah, right. Right. That thing, right. You're right. So in that case, you will see that this pseudo inverse will be equivalent to basically this case, right, that we saw. So the matrix essentially the vector lies in the column space, right? So for this B, right? We saw this example. You remember this? If you have
Right, right.
a
Yeah.
unique solution, right?
Mhm.
And then if it is not lying in this space, then you will have to take the uh, projection, whatever. Now, if you take the projection of this vector itself, you will get the same vector again, right? So that's not a problem. Fine.
Okay. Okay. Oh, okay. So I can phrase it in this way, I think.
So let me
Suppose I have this
clarify. There
matrix.
are there is a
Yeah.
difference
Yes. Yes.
in yeah. Let me clarify. There is a difference in the two matrices. These two matrices are not exactly equivalent. When m is greater than n, the situations are different. When m is less than n, the situations are different. When m is greater than n, you have more information, so you have more points to fit on a straight line or on a plane, which is not possible. So you project all the points on the plane, right? So this is the case when the matrix is tall, m is greater than n. Fine, is this clear?
Right, yeah. Yes.
This is straightforward, right? We don't need to think of tall matrices after this. You are
Right.
getting a very large number of points. So this is one way of looking at, but the other way is you have a small set of you have m dimensional vectors, and you are choosing let's say n such vectors such that n is less than m, and all the vectors are linearly independent and linearly independent m dimensional vectors, and you are adding them up, taking their linear combinations to form another m dimensional vector. Now, if you are doing this, there is a possibility that this m dimensional n vectors will form a plane, and if you are trying to reach to take a linear combination of these vectors that lie in this plane, then you will have a solution, right? But if it does not lie in the plane, it is outside the plane, then you don't have a solution, right? You have zero solution in that case because it is not in the plane. Then for that case, what you have to do, you have to take the projection. Is this clear
Okay.
for tall matrices?
Yes. This is
Sir, excuse me.
Hmm.
If we take one example, is one example, and then we'll try to solve. So I think the concept will be more clear because theoretical things. So I think it's
Hmm.
if you take the example and then we can understand little bit also. Like if we'll try to solve, let it be the answer will be whatever it is, but we can get the some idea that
So let me take the XYZ plane, right?
cross to,
You have
and let's try to
YZ, right? Now let's say my systems of equation is like this. X plus Y equals to 0, 2x plus 3y. Also x plus y equals to 10. Let me put it 0 here. So 0 and 2x plus 3y equals to 1. Let's say we have these two equations, right? Let's plot the lines, or we can always solve. There are multiple ways to solve this. Let's write it as a system of equations, right? System of equations. So you can write it as 1, 2, right? You have two equations, and the column vectors
so
are
the z
1, 2,
component is 0
3.
you're considering.
Yeah, yeah,
Okay.
yeah. 1, 3, 0, right? So you have these two vectors, and using these two vectors, you want to span the plane, right? And the solution is 0, comma 1, comma 0. Right? Now this is your A, this is your X, and this is your B. A is belonging to 3 cross 2, X belongs to R2, and B belongs to R3, right? Now the thing is, you are taking two three-dimensional vectors, and the vectors are 1, 2, 0 and 1, 3, 0. You are taking these two vectors, so 1, 2, 0, multiply it with some scalar, plus the other vector is 1, 3, 0, and you are trying to span a space using these two, right? The question is, what is the space that these two vectors span? You can always say that 1, 2, 0, where this vector will lie. This will lie to 1, comma 2 here. So this is your first vector, right? And the second vector is 1, 3, 0. So 1, comma 3, right? So this is your second vector, right? So this is your second vector. Now using these two vector, which space can you span? Can anyone tell me?
R2 only. I think it will be in the XY plane only.
It will span the XY plane. So if you use only two vectors, that two three-dimensional vectors, you will span only one single plane in the three-dimensional space. Now, let's say you have any vector that has some positive or negative z component, some non-zero z component, then you won't get a solution, right? Is this part clear?
Sir, I have a little bit doubt with the system of linear equations part, how you wrote it in the matrix form.
Hmm.
So I was thinking that x plus y plus 0z equal to 0 and 2x
Hmm.
plus 3y plus 0z equal to 1. These are the two equations.
Hmm.
So out of these two equations, the matrix I formed, it is 1, 1, 0, 2, 3, 0 in next to next rows.
No,
So
no,
it is a,
no, don't consider it like this. I am sampling vectors from the R3 space, right?
okay,
So let's think of only this kind of matrix where I'm sampling vectors from R3 space. So when you talk about R3 space, your basis has to be belong to R3, right?
right.
And you can always say that the third equation would be 0x plus 0y equals to 0,
Okay,
right?
okay,
That is what I've done here.
okay. Got you.
Fine. So from here you can see this. Now the question is, let's say if I choose a vector, can we reach this kind of vector 0, 0, 1? Can we? The question is, can we do this?
No,
No.
okay.
No, right? So then what you do, you take a projection, you apply projection to it, and you will get 0, 0, 0 as the solution. Or let's say if we have vector 1, 1, 1, what you do, you take a projection. That is your least square solution, which will be 1, 1, 0. This is how you do it, right? This is what happens for tall matrices. Is this clear, everyone?
Yes, sir, yeah. Uh, Sir, the doubt I had with the pseudo inverse part. So,
Yeah.
can you scroll a little bit upwards? Where you took, yeah, right, that where you took that 5 by 3 example, 1, 0, 0, 0, 1, 0.
Hmm.
Right. So, for this particular tall matrix, the last two equations are redundant. So,
Hmm.
if someone thinks that if we consider only the linearly independent equations, that is the first three, which are essential equations. If we only
Right.
consider them, and so we can find the pseudo inverse of this matrix, right? Pseudo inverse can be found for this matrix.
Hmm.
So I was trying to establish a relationship between the pseudo inverse and the inverse of uh, this matrix, taking only the first three rows. So is there
Okay.
exist a prominent relationship? Because the first three rows, I think they are making the impact. The last two rows, they are just generated by the first three rows. So I was trying to think
Or
whether,
the opposite, right? Or the opposite. You can choose last three and then first two rows will
right,
be
we can.
redundant versions of those. So you can always do RREF of take R. You should always take
Yes,
RREF
yes,
of this,
right.
and then you will get the top 3 by 3 block.
Right. So is there a relationship between the pseudo inverse and taking only the three rows from here, building a matrix and taking inverse of that?
So essentially, when you are removing 3 row vectors from here, right? So you are jumping from R5 space to R3 space, right?
Right.
You are jumping from R5 to R3 space. For example, in this case, you are simply ignoring the third equation, and you are jumping from R3 to R2. So you are going to 1, 1, 2, 3, xy is equals to 0, 1, right? Now, any vector or matrix operation done this in R2, you cannot like relate it to something in R5, right? You are extending the basis and then you are going into R5. Fine.
Um, okay, so the sizes of the pseudo inverse and this matrix will be same, right? The pseudo inverse will be of size uh, 3 by 3, I think.
Yeah,
8
right.
dagger or 5 by 3 would be
Yeah.
okay. And what will happen if I take only 3 rows? The size would be also like 3 linearly independent rows I selected, and I took the inverse out of it. So it will also have 3 by 3. So I was thinking whether there exists a relationship between them or not.
Hmm. Right. This will be 3 cross 5, right? Pseudo inverse will be.
Uh, oh, oh, okay, right. Yeah, you're right. Sorry.
Right?
Yes, my bad. Yeah, right.
Because you are dealing with five vectors in the R5 space, and then suddenly you cannot directly say something on R3 space, right?
Okay, right. Yes, yeah.
Fine. Okay, that's it. Fine. So this was a simple case for when the matrix is tall. Now, when the matrix is wide, then things change, right? So let's say your matrix was a wide matrix. Let's consider the same example. Instead of R3 space, I am sampling R2 space using three vectors, right? The first vector is 1, 2, 1, 3, and then 0, 0. And then x, y, z is equals to sum b, right? Is equals to sum b. Fine. So now you have chosen vectors from R2 and you have chosen three vectors from R2, right? And we all know that only two are sufficient to span the entire R2 space. The third one will be a redundant one, right? So it will be a linear combination of first two, right? We all know this. So uh, the question is, how many linear combinations exist? Can anyone tell me?
These are independent.
So
So
let me remove this 0,
one.
0. Let's put something 1, 1 here, right?
Oh, then so infinitely many will be possible.
Right? Infinite many possibilities. Now you have infinite many solutions and you are trying to find one
like
solution.
uh,
Yeah.
I have doubt now.
Hmm.
Again, for the solution, it depends upon the B that what it is. Then only we can say, no, directly we can't say anything. Because if we like if you if I'm
Right.
ignoring this all.
B dot y should be 0 where y belongs to null space of A transpose,
Mhm.
No,
right?
but here B is coming from R2 and the columns are enough to produce any vectors in R2. So B will always lie in the column space. So no
Yeah.
need to check any condition. You'll always have a solution. Now the thing is
Yeah.
to look whether unique or infinitely many. And since we have a free variable, so it will always have infinitely many.
What I'm thinking ki, if B we are going to take and I'm going to apply the Gauss elimination method by that also, I think it will not, it won't work, or because they there the things will be more clear, I think. Because if you forget this one concept also, pseudo inverse, and if you take B any vector.
Yeah, right. It essentially depends on the B, right? Let me frame it like this. So it's a 3 by 2 matrix, right? So its range is R3, right? एक, two, 3 by 2.
Range will be
Oh,
R2.
sorry, 2
Range
by
will be
3.
R2.
2 by 3. 2 by 3. Sorry. range is R2. Let's go back to the fundamental rule, right? 2 by 3 matrix, right? So R2 is the range, and this will be orthogonal to the null space of A transpose. Now my question is, let's say uh, uh, what is the null space of A transpose? Null space of A transpose will be essentially whatever will be the null space of what is null space of column space of A transpose, right? Now the question is, if you have at least two linearly independent vectors in matrix columns, if you have these at least two, right? I mean, it you have only two, either two or one. You cannot have three for this case, right? Now, if you have two linearly independent vectors, then what is the null space of A transpose? Anyone?
I think empty space will be there.
Right.
Null
So
space.
this will be empty. And now I'm saying you want to solve for A x equals to B. Then where B can lie, you are taking a linear combination of these two vectors. Where it will lie?
It is not necessary that it will lie in the R2 space. It can be in between also, no? Like R2 and null space, both are perpendicular. In between also, it can lie, no? So we can project in that R2 space. That scenario will be not there.
Okay, Ajay, you are saying that thing. Let me do this. Hmm. No, but R2 space is the general canonical space, right? And you have as many vectors as you want to span the entire space. So then, what is the extra space where you are getting this?
Uh, just I'm thinking like both are perpendicular. Like uh, uh, where in between, no, we have like what we have done in the column matrix, no, we have projected, like if the solution is not there, then we have projected in the column space that p
Right,
vector.
right. But that's fine. But my question is, how can be in R2 as well as empty?
No, I'm
How
not saying
can
it is in the uh, okay, it is not necessary that it will be in R2 or empty. It can be anywhere, no, in between also, like because if we take the basis of both, no, I think we can in that space also it can be represented, I think so. Like
Okay, I think
what
I
we have.
got Satinder's doubt. Can I say, sir?
yeah, yeah, yeah.
So
Good.
I think Satinder, just confirm me whether you're thinking like this. So you have a horizontal page in front of you, and you have a perpendicular page on that. So you're thinking there might be vectors which are not in the horizontal space as well as not in the vertical space. There might be
Yeah, you're
vectors,
right.
right? So, but in
Yeah,
orthogonal
that
complement,
one.
right? But in orthogonal complement, these two planes can never be orthogonal complement to each other. So their dimensions have to add up to the total dimension. They might look orthogonal. That part is true. These two pages that you are thinking right now, that one page vertical page, one horizontal page, but these two are not orthogonal complement subspaces to each other. So this
Mhm.
space is R3. When you have the page, horizontal page in front of you, it has dimension through 2. So anything which you will call orthogonal complement to the horizontal page has to have the dimension 1. It cannot be a
Right,
so
right.
in this case, if it is not in the null space, left null space, it must be in the picture looks as if there is plenty of space apart from this column space and left null space. There might be plenty of things. Um, am I right on this, or like
Yeah, you
for
you
this part?
you're thinking it correctly. I mean, you're right. So the way you Satinder is trying to think of this is, let's say you have a R3 space, and then let's say I am spanning considering the XY plane as the range space. Now, what will the null space of the XY plane? Basically, if you are only considering the R2 space, it will be an empty space, but you are considering the R3 space, you have this something along the Z axis, right? But you cannot have this XZ space as a null space of XY space, right?
Right. For this part, it is right. So, sir, tell me what will happen if the column space is not entire R2. Suppose the column space is a one-dimensional space,
Mm.
and the left null space is also one-dimensional.
Yeah, right. That is possible. So then this matrix won't be a full rank matrix, right?
Right. So in that case, can Satinder have a vector which does not lie on the column space as well as the left null space? So he's basically asking, is the in that case, is there a possible? Is it possible to have a vector which does not lie on the column space as well as the left null space, but it is made up of these two? So maybe summing the two vectors from column space and left null space.
Let's say we have this matrix, right? So, and you have XY, and you are trying to span XYZ, and you are trying to span B1, B2, right? Now, the question is, what is the space we are spanning? We are spanning this into this. X plus Y plus Z equals to B1, and you are spanning X0 plus 0 plus 0 equals to B2. This gives you constraint that B2 has to be 0, right? So you are saying that can we have a vector that is not in the null space as well as in the range space, right?
Right. Left null space as well as in the range space or column space.
Okay, since they are orthogonal, can we have vectors in between these two? Okay. Mhm. Mhm. So what will
So
be the
here the
range
columns,
space?
it is
Yeah.
1, 0.
Right. And the null space is essentially 0, 1, right?
Left null space you are saying, right?
Left null space, yeah.
Left null space, yeah, it is. It should be 0, 1, right? Is it? Is it? Just let me.
Yeah. It's oh,
Right.
sorry, null space is in the input space, right?
That's why we're looking at the left null space, right? Column space and left
Yeah,
null
null
space.
space will be the input space, and then
Mhm.
left null space will be 0, 1, right? And the range space is 1, 0. And the question is, can we have a vector like 1, 1? That essentially lies neither completely in null space nor in the left null space and nor in the range space of the matrix, right?
Right. That I think that's what was confusing Satinder. So,
Okay.
but in the previous case, it wouldn't have been possible because the entire R2 is in on the other side and null
Yeah,
like
right. Yeah, that's why I'm saying that these are two linearly independent vectors in the matrix, right?
right. Yeah.
So is this clear, Satinder?
I think he's facing some problem, so he left some network issue or maybe something. So he just
Okay.
left right now.
Okay,
I think he
so
will join back. Yeah, it's clear now.
okay, fine. So yeah, so let's see if he comes back, then we will resume. But is everything
Yeah,
clear
sure.
here?
Yeah, yes, sir. Clear.
Okay, let me take a break for 2 minutes. I just need
Sure.
I got a message from someone.
Yeah, sure, sir.
Yeah, so let's resume. Fine. So, hi Rohan, are you there?
Yes, sir. Yeah.
Fine. So, is this clear? Any doubts in this?
No, sir. It's completely clear.
Fine. So, this was this. Now, the question is if the matrix is wide, then you need extra information to take the projection because you have infinite many solutions. Then you need one more condition to define what is the solution, what kind of solution you want, right? So, this is basically what I think has not been covered. Has it been covered in the lectures?
I don't think so.
No, right? Because essentially, if you have, let's say, 10 solutions, then you have to choose one among them, then you need some condition for that, right? Okay. So, yeah. So, that is also known as method of underdetermined least squares. So, I think that will be covered later on, whatever, right? So, yeah. So let's move on to the next thing. What are projection matrices? So as we saw that oh sorry, we saw that these matrices are essentially known as projection matrix. But what are projection matrices? Now let's say I am only dealing with orthogonal projection for now. You can discover other projections later on. So let's choose orthogonal projection, right? So what if let's say we have a matrix P that we say that it is a projection matrix? What is the property that you want to think of?
So P square equal to P was very natural to me because if we have
Right,
projected it one time, then it is already in the space. So no matter how many times more we do, it will still be in that space.
right. So it has to be idempotent, right? Or an idempotent matrix is essentially a projection matrix. Now, the second criteria, P transpose, the P has to be symmetric, comes from the orthogonality condition. So if you are choosing orthogonal projection, then yeah, the matrix must be symmetric.
Right.
How?
Sir, this part now.
Hmm.
Yeah. Sorry. Go on. Go ahead, sir. Yeah.
So you have a doubt in this?
Yes, sir. I can. Should I ask it now or after you
You
cover
can
this?
ask. Yeah, you can ask us.
So P square equal to P is very natural to me. And when
Yeah.
I saw P transpose is P, it is valid
Hmm.
for because I can easily do the transpose operations on that projection matrix. And I found out that yeah, indeed P transpose is P. But I was trying to associate the idea of orthogonality with the transpose. So how
No,
can
P transpose
something of
equals to P is only for orthogonal trans projection only.
yes, sir. So that was not coming very naturally to me. I just computed it and found out that P transpose is indeed P, and that's why by definition we call it symmetric matrix.
Hmm.
But
So
how
you,
symmetricity arises from orthogonal projection,
yeah, yeah.
maybe we
So
can visualize it.
yeah, so let's say you have this. This is the range of a matrix, right? And you have a vector that looks like this, and you want to project it, and you want
Right.
to take an orthogonal projection, right? So now this will be your projected vector, right? The black one. So
Right.
what is this vector? This difference vector. This is essentially uh pu minus u, where u is this vector, right?
Yeah.
And this vector is pu, right? Now you know this that pu, this vector, this orthogonal projector, this is the orthogonal line, right? So you know that pu minus u belongs to is along the normal of the plane, right?
Right.
You can always say that. And we know that any vector belong to in the range space of A, dot product with the normal vector has to be 0. And then from here you can figure out that pu minus u dot pu is equals to 0. And then from here you will see that you will get this condition which says p transpose, oh sorry, you will get this condition that p transpose p equals to p square. And since p
Right.
transpose p is symmetric, p has to be symmetric. And then
Okay. Yeah. So this calculation I understood. I was thinking it in this way that so projection matrix is basically a matrix which so this matrix represents a transformation, right? So
Yeah.
earlier the U vector, which was not in the column space, I multiplied it with a matrix and suddenly it became in the column space. Now, when I'm saying that P is symmetric matrix, it means if I take the transpose of P and if I still multiply it with that vector, it will do the same operation. So just because I don't have a geometrical interpretation of transpose, so when I take transpose, what happens geometrically, that thing is not clear. So that's why I was unable to see why, even if we are taking the transpose, it is still doing the same job. Why it is not taking it to some other plane or somewhere else. So that part, the computational part, I understood, but uh, so I was unable to understand that because I don't have a geometric interpretation of transpose. So what happens in case of transpose of a matrix, how it changes the transformation? I don't have the idea of that. So I think if I can have the geometric interpretation of transpose, then I'll be able to see it uh, more clearly. Or yeah. Am I able to express it to you what I'm thinking?
Yeah, right. You are right. You are right. Okay, fine. So basically, can we do this? Do something using this? The fundamental spaces here.
We can think.
So let's say we have a vector that belongs to the range space of A, and then we have a vector that belongs to the range space of A transpose, right?
Right. Okay.
Then first thing, if you have the idempotent property P square equals to P, then P has to be a square matrix, right?
Yes,
And
indeed.
second thing is, should it be full rank or not? P square
Not
equals to P.
necessarily.
Hmm. Let's see. Let's say if I take this matrix 0. So now this will project everything in an XYZ plane. So let's think of this. So let's take this projector. So will this is this a projection matrix? Let's check. So 1 1 0 0 0 1 0, right? So right, this will be 1 0 0. This is 0 times this plus 1 times this, 0 0 this, so 0 1 0, and then again this is 0 0 0, right? So yeah, this is a projection matrix, right? That projects all the vectors onto the
Right.
XY plane, right? So now, so you have column 1, column 2, and column 3. Now when you transpose it, you get column 1, column 2, and column 3, right?
Yes.
I can't think of a some geometric interpretation of transpose from here.
I think when we are taking P transpose into P, something like that, so that converts into orthogonal projection. That is the concept, I think, or diagonalization of the matrices. That concept is also there, I think. And it is
Diagonalization is
possible.
something. Yeah.
The projection concept is related to the symmetric matrix only. So when we are taking a P is not symmetric, so when when we are making a symmetric matrix like A into A transpose, that will be always symmetric. And one more condition is there, like A into A transpose is orthogonal matrix if it is equal to I think that's why if A into A transpose is I, so that is orthogonal matrix.
But
That definition is
orthogonal
also
projection and orthogonal matrix are different things.
So Satinder, actually we are thinking why we are trying to find a geometric interpretation that why orthogonal projection has something to do with symmetricity. Mathematically, we already have figured it out. Now we are trying to find, basically we are trying to find what happens when you take the transpose.
Oh. So it becomes obviously. Right. So I don't know. I mean, it's not straightforward right now.
Yeah.
We can't say directly. Hmm. We can think of the null spaces, but since it's a square matrix, then if it's a full rank matrix and a square matrix, then column vectors and row vectors span the same space, right? Same space, right? So when okay, then when you will do the matrix product A into U or A transpose into U, right? So what happens here is A transpose U. Yeah, right. It's not directly inherently clear what is happening, but AU is basically a linear combination of columns and AU. So let me see if I can find something quickly. Right.
Sir, if A is not symmetric, then
Ah,
AU and A transpose U will also not be same, right?
then they will be different, right?
They will be different. So can we argue it from this side that so I'm trying to do the reverse engineering. So I'm trying to say that uh, if I multiply it with A, that is AU, and if I multiply it with another matrix B, say BU, and I'm saying that both your matrices do the same job. So if I so both the matrices are projection matrix, and they will do the orthogonal projection. So AU and BU will be same. Uh, so um, so is that required that taking or so I was trying to say if A is not equal to A transpose, basically AU and A transpose U would not be same, and that's why they won't be projection matrix or something like this. I was trying to argue.
Okay, fine, but yeah, right. That is true. Like if AU equals to A transpose U, then basically you are saying I am projecting it. Yeah, I have this and I am taking the orthogonal projection. I am projecting here. So let's say this operation is AU. Then what is the operation AU, A transpose U, right?
Right.
And what does that say? I mean, I'm not sure what does that say, right? I mean, mathematically, we can prove that A has to be equals to A transpose. Basically, it says that A transpose A equals to A, which means A has to be symmetric. And then which means, let's see if I write U sigma V transpose, and then A transpose A will be V sigma transpose U transpose, V sigma transpose sigma V transpose, right? And then this will be the basically eigenvalue decomposition. And then if you take the transpose of this, you will get V sigma transpose sigma V transpose. And these both are same things.
I was also looking in the internet, but I found that directly transpose has no easy interpretation. Some
Yeah, transpose
interpretation
not
are there,
directly. Ah,
yeah, like with using the adjoint operator in linear transformations.
hmm,
So they are using the adjoint and that's idea to
hmm.
interpret in some sense of transpose. But I was unable to read it, so I was not understanding it properly. That's why I left it there. So,
Yeah, right.
sir, yeah, if you have some time later on, like after this course, when
Hmm.
if you have like 5 or 10 minutes, then I can show you that picture. So it's from that book actually, Linear Algebra Done Right by Sheldon Axler. So
Okay.
in that book, he has given some sense with the relationship between adjoint operator and transpose.
So you
So I will
can
send
post
you.
the image in this answer chat box right now.
Yeah, right now I don't have it, but I will send it here then after
Okay,
this session.
fine. Yeah, yeah,
Yeah.
right. So let's discuss that later on, right?
Okay, okay, sir. Sure. We can continue.
So this was it about projections, and then you know this simple formula on how to define a projection vector on another vector, right?
Yes, sir. Yeah.
Fine. Now there are some properties of pseudo inverse, which is pretty straightforward. Essentially, A into A pseudo inverse of A into A is equals to A. And these two properties you can simply verify directly, right? Everyone,
Yes, sir. Yeah.
right? And then there is some property of square matrices. If it's square matrix, then A dagger will be A inverse. For tall matrices, this is the formula. For wide matrices, this is the formula. And then if it's A is a projector, basically a square matrix, 8 dagger equals to A, right? This is all clear, right, everyone?
Yes, sir.
Fine. Considering the full rank property, right? Now, the last topic that was covered is eigenvalues and eigenvectors. So we already saw this part, right, earlier also, how to get the eigenvalues and what kind of eigenvalues you can get, right, everyone? Is this clear? AU equals to lambda U cannot be zero, right? Everyone, do you have any doubts in eigenvalue and eigenvectors?
No, sir.
Fine. Then there are two interesting properties that were covered: algebraic multiplicity and geometric multiplicity. So the algebraic multiplicity says that so these two properties are always associated with given eigenvalue, right? Let's say you get some eigenvalue for some matrix A, right? For that eigenvalue, you can define two properties. One is algebraic multiplicity and one is geometric. So algebraic multiplicity is number of times the eigenvalue is repeating in the solution, how many times the same eigenvalue is occurring. And geometric says number of linearly independent eigenvectors associated with a given eigenvalue is called the geometric multiplicity. Fine. So these are two definitions, and we will see what it means and why do we require this. Just know that there are some definitions here, right? We know that we can have multiple same roots for these characteristic equations, and then from that we can define the algebraic multiplicity, and then each eigenvalue essentially spans a space, right? So let's say you have some lambda, then you can say a x a lambda AV equals to lambda V, right? So A minus lambda into V equals to 0. Then the null space of A minus lambda V is itself A minus lambda I. A minus lambda I is itself is a null space of this itself is a space, and few vectors can span that space, and that gives us the idea of geometric multiplicity, right? We will see what it means, why it is useful, but just know what is the definition of diagonalizability, right? So let us consider a matrix with an eigenvalues and eigenvectors associated with them, and then let P is equals to eigenvector 1. P be a matrix containing all the eigenvector 1 as their columns, eigenvector 1, eigenvector 2, eigenvector n. First of all, what first question: how many eigenvectors can we have
Um, for which matrix? M by
for
n or
any
For square
n
general
by
matrix
n?
matrix?
only.
For square eigenvalues are defined for square matrices, right?
Right, right, right. In many, at most n.
Right, and at most n linearly independent eigenvectors can exist, right? Everyone agrees with
Right.
this. Fine.
Yes, sir.
Fine. Now, let's say we have a matrix P that contains all the eigenvectors as its columns. then we can always say that AP equals to A eigenvector. Can you see this pattern here? AP equals to A into eigenvector 1 is the first column, dot 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 A into eigenvector n as the last column. Is this clear, everyone?
Yes, sir.
Now,
Yes.
do we know that what is AV1,
Yeah, lambda 1 v1.
right? So we can write this LHS as eigenvector 1 dot 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 eigenvector n multiplied by a diagonal matrix containing the eigenvalues on the diagonal, others are 0, right? So this gives us this pattern AP equals to PD. Now, since we are saying that all the columns of P are linearly independent, we can define P inverse, right? Everyone, do you agree with this?
Yes, sir. Yeah. Right.
Then you can say that A equals to PD P inverse, right? Now here what we have achieved is the eigenvalue decomposition of a matrix A. Using the simple properties of eigenvalues, we will see what does this mean, right? We will see what is happening here. But this is pretty clear, right? What does this mean? Does this exist for all kind of matrices? Is there a set of matrices for this, for where this is defined or not? These kind of things we will see. Right, everyone? Do you have any doubts in this?
No, sir. Clear. Till now.
Fine. Yeah. So how to think of this multiplicities, simplicities is something that you should think of, right? So basically what I'm saying is, let's say you have a some vector AV equals to lambda V. Then I'm saying A minus lambda into identity into, I'm rearranging the equation, equals to 0. So let's not go to the characteristic equation from here. Let's try to see what is it is saying. It is saying that V, since and V is not 0, right? V is non-zero. Then V belongs to null space of A minus lambda I, right? Everyone?
Yes, sir. Right.
Now, if A is n cross n matrix, what is the maximum possible dimensionality of, obviously non-zero entries? Then what is the maximum possible dimensionality of n A minus lambda I?
N only.
No, no, n minus 1, right?
Um,
There will be at least one dimension in the range space of A, right? A minus lambda I, if it is not containing non-zero entries.
okay.
At most n minus 1. No?
But
Yeah,
A can be if I'm thinking about A to be identity matrix. So
then 0. Then the null space is 0, right? 0 dimensional. I mean, sorry, null space contains 0 vectors. Is a seeing empty set, right?
oh yes, sir. Right. Right. Sorry, sir. Yeah. Right.
I'm talking about A minus lambda I. Acha, you are saying A is directly equals to identity, right? And lambda is 1.
Yes, sir. Yeah.
Ah, I get you, right. So let's ignore that thing. Let's not think of that. First, let's think of this null space of A minus lambda I. Let me say that A minus lambda is A minus, let's say A minus lambda I is another matrix B. Then what is NB, right? NB is itself is a subspace, right? Can we prove this?
Yeah, we can.
Right? So basically null space of B will be vector subspace, right? Vector space, basically, we can prove this. Then, since it's a vector space, you can define some vectors spanning this space, right? Vectors that span this space, right? Is this clear? Note
Yes.
that here lambda is fixed.
Yes.
Lambda is fixed. We are not considering all the eigenvalues. For one particular, I'm choosing one particular lambda, one particular eigenvalue, and I'm trying to observe the properties of this null space, right? So there can be vectors that span this space, right? Is this clear?
Yes, sir. Yeah.
Fine. So how many vectors can span an n minus one dimensional space? There can be more than one, right? It can be a line, a
Yeah.
plane, right? Or a hyperplane. depending on the dimensionality of matrix, right? Fine. So that dimensionality, like the number of linearly independent vectors that can span that space, is essentially the geometric multiplicity of that fixed lambda value, right? Now, is the concept of is the definition of geometric multiplicity clear,
Yes,
everyone?
sir. Yeah.
Right? You can have multiple vectors that lie in the null space of this matrix P, right? So yeah, this is the idea of geometric multiplicity. Then algebraic multiplicity, I think you all are familiar with. Basically, how many
Yes.
times of the
Repeated,
root is
repeated,
repeated,
repeated eigenvalues.
right? So this is pretty clear. Yeah, this was this for eigenvalues, I guess, right? Now, yeah, again, since if you want to discuss what are diagonalizable matrices, what is the property of diagonalizable matrices, right? Then you can always say, right? Uh, all the eigenvectors have to be linearly independent, right? So the total geometric multiplicity should be how many? Anyone?
Equal to algebraic multiplic. Total algebraic and geometric will be equal, I think. AM equal to
Equal to
GM.
n. Equal to n total geometric multiplicity.
It should be equals to n, right? You can have repeated root with, let's say, two repeated roots with geometric multiplicity is equals to 2, right? So basically, geometry sum of geometric multiplicity has to be equals to n for it to be diagonalizable. Diagonalizable. And then, yeah, you are right. So then, like, we will see that what are defective matrices and why they can be diagonalized. Then we will see what is the relation between AM and GM, right? We will see the proofs, if even if you, whatever you are claiming is true or not. I'm just saying, from a basic brute force way, can you see this? Like, if I want to write the matrix slash PDP inverse, you want the P matrix as which is the matrix containing its column vectors as the eigenvalues of the matrix. Then what is one observation you can always say? You need to ensure that there are n linearly independent eigenvectors, right? And then geometric multiplicity says number of linearly independent eigenvectors associated with a given eigenvalue, right? Then what is the number of linearly independent eigenvectors? It has to be n, right? So we will see what are defective
Like,
matrices and what are the relations between
like
them.
here, beforehand, P, how we can come to know ki, okay, it is eigenvectors, like beforehand only, or like P matrix, like you have written beforehand only uh, E EV1, whatever it is. P matrix, what you have taken? You have taken for the eigenvalues. So,
Right.
so beforehand only, because we have to first of all calculate, then only we can form that part, no?
Yeah, right. You need to know the eigenvalues, then only you can say. Yeah, right.
Mm. And one thing more, like if like to diagnosable, I think the matrix should be symmetric. Then we can make it like then only it can be diagnosable, I think.
No, if it
That
is
is
symmetric, then you will see that it will be the eigenvectors will be orthogonal. It has nothing to do with diagnosability.
okay. Okay.
A matrix can be asymmetric and then still be
Okay.
diagnosable.
Okay. Okay. Thank you.
Fine. Any other question? Fine. So this is all that was taught in lecture week 10. So I think I did not have enough time to solve the problems on this. So what I'm going to do is I'm going to share the problems for week 10 with you guys, right? So can you solve this for me? And then tomorrow there is an extra session. If you are free, you can join and then you can simply give me the answers to these problems. And then
Sure,
if you
sir.
have any doubts, huh?
Sure, sir. Sure.
What will be time, sir?
So the extra the announcement is posted on the course page itself. It is between 3 to 5 p.m. Starts at 3
Okay.
tomorrow. So I will just try to finish up everything from lectures week 10 and week 11 tomorrow.
So
Okay, sir.
what you're
Fine. So
sharing this one, so from where we can download this one, or if you're
the
sharing
link
this
must be
part?
shared with you guys, right?
Okay, this page one, what you have.
Huh. Huh. I think there is a link to all the video lectures and uh, s- uh,
Yes, sir. Just
this class notes, right?
Okay, okay.
right.
So there we can go.
Yeah. So I'm just sharing this problems for week 10 also, right? And I'll be sharing the problems for week 9 also.
Okay. Like, sir, one request is also there. Like, whatever the topics we have covered so far, like now it is
Hmm.
going to end, I think.
Hmm.
So, because we are in the 11th, I think, week,
Week.
and it is
Yeah.
of 12 week only. Like,
Yeah.
if we get like 15 or 10 questions or 20 questions to solve, so we can get the proper understanding part. Like theoretical part, just no, what is happening for the sake of just passing, or just we are learning. Means just total concepts are not very much clear. Like because we want some of the questions also to solve it, so that we can get the clear picture of the things. Like what the book has been recommended, I think it is totally theoretical, and examples also are not that much. I think what I've gone through the book, because when we read the book by ourselves now, so we can't understand. Like when you are explaining, or when we see the lectures now, then the concepts are clear that you actually what it is written. Because by our own, when we are reading, so nothing we can understand. It's not a single line also.
I think the book by Gilbert Strang has a lot of problems. You can take
Okay,
that book and on the
okay,
you will find the problems in that book itself.
okay, okay, sir.
Yeah. Yeah, so I have shared all the PDFs, right? So try to go through the problems for today's session and we will try to cover this part in 20 minutes tomorrow, right?
I think that has been also covered in this one lecture. Quadratic forms also, I think it was there.
That I will cover tomorrow. Like for week 10, these are the problems for week 10, very simple problems.
Okay,
I think
okay.
you guys can finish this.
Sure, sir. We'll try. Yeah.
And I'm also sharing the week 10 notes. Fine. So thank you all. So
Sir,
session is over.
just a sec. Uh, hey, Satinder, I have shared my email ID here. You can ping me once. I have another book called David Seeley. The exercises are very nice, like easy, moderate, and then difficult. All kind of varieties are there, and lots of examples are also there, apart from Gilbert Stein.